My name is Ayşegül. I'm an operation researcher at Structured Decisions Corporation in West Newton, Massachusetts. I develop mathematical models to analyze complex logistical operations. Today I'm excited to tell you about linear programming and how it helps us make decisions in our daily lives. Before starting to explain to you what linear programming is, let's first look at what programming is before putting the word linear in front of it. In our world here, programming is not computer programming. For us, the word programming means planning. Programming problems is basically a systematic way of making decisions. It's like designing a program for a vacation day with your family or friends, which activities to pick and how to schedule them. Let's face it, each morning we all encounter a programming problem. Getting dressed. Let's assume I'm putting on 4 items of clothes: pants, shirt, shoes, and socks. In all the different ways I put on these clothes, which order will minimize the time for me to get dressed? That is my objective. Work with some other students in your class on this and come up with an answer. I'll see you in a few minutes. Welcome back. So how many different ways did you come up with? Well, there are 4 times 3 times 2 times 1 equals to 24 different orderings. However, can I wear socks over shoes? Not really. Or putting on my pants after putting my shoes on will be really tough too. Therefore, many of these orderings are impractical programs, meaning that they either do not match with society's standards or are not efficient, which are my constraints. So let's eliminate some of these orderings. But hold on a second, I still have a large number of them. So how do you choose which one is the most efficient? In other words, which one is the optimum? And remember that each ordering has a degree of effectiveness that enables me to compare them so that I can select the optimum one. Also, do not forget that you might add other limits, or again, in other terms, constraints to your problem, such as the number of drawers you open and close, let's say to minimize the noise. Next, let's move to the term linear. If some things can be linear, that implies that others are then nonlinear. Here's an example. Let's say we are buying socks in a department store. If a pair of socks costs $2 and there are no discounts, then we can say that our total cost is directly proportional to the number of pairs we purchase, meaning that we pay $2 for a single pair, $4 for 2 pairs, and $20 for 10 pairs. Here, our total cost is linear with respect to the number of pairs we purchase and looks like this. On the other hand, if there was a 20 cents discount for the second pair, 40 cents discount for the third pair, up to the fifth pair, and $1 afterwards, then our total cost will be nonlinear and looks like this. In short, linear programming problems are really programming problems where all the mathematical relationships can be represented as linear functions. So what kind of mathematical relationships will we have in a linear programming problem? Well, we will have 2. First, an objective function to maximize or minimize, and this objective function indicates what we want to do, like minimize our annual cost of travel or maximize profit in our business. Second, there will be a set of constraints that have to be satisfied in our solution. Well, we will illustrate these concepts by an example in the next segment. But before that, discuss with the person next to you and see if each of you can come up with examples of both linear and nonlinear relationships. And also determine some of the mathematical relationships in your own examples. See you in a couple minutes. Welcome back. So were you able to come up with some examples? Well, the diet problem is one of the many classic applications of linear programming studied back in the 1940s. It basically involves finding a group of foods, a diet, that meets all daily nutritional requirements at minimum cost. One of the early researchers who studied the diet problem was George Stigler. That's why it's sometimes called the Stigler diet. George Stigler was a 1982 Nobel laureate in economics, and he posed the following problem. Let's assume a moderately active man who weighs 154 pounds. He has a list of 77 foods he can eat from, and his goal is to satisfy the minimum daily requirements of 9 different nutrients while keeping his expense at minimum. He wants to figure out which of these 77 foods he should eat and in what quantities. Back then, Stigler wasn't able to use computers to solve such a problem. So he used his intuition to find a solution. Here, his objective function was to minimize cost of food, and his constraints were all the dietary requirements to stay healthy. The first thing Stigler did was to eliminate, through trial and error, 62 of the foods from the original 77. Well, they lacked nutrients in comparison to the remaining 15 anyway. Then from the reduced list, he calculated the required amounts of each of the remaining 15 foods he needed to minimize his cost. So what do you think he came up with as his annual minimum cost? Well, in $1939, the annual cost of his solution was $39.93. In today's dollars, this will be about $600. Well, that is pretty inexpensive. Unfortunately, the Stigler diet has been criticized for its lack of variety and palatability. But the good news is that his method had received praise and recognized by his peers. In 1947, 8 years after Stigler made his initial estimates, George Danzig came up with an algorithm called the simplex method to solve linear programming problems. He showed that Stigler's diet problem was indeed a linear programming problem, and using the mathematics and the original 1939 data, he determined the true annual optimal cost using his method to be $39.69. Well, Stigler's guess for the optimal solution was off by only 24 cents per year. In the early 1950s, Danzig decided to use Stigler's method to solve his own diet problem after his doctor advised him to go on a diet to lose weight. So he modeled the problem and let the computer decide what he would actually eat each day. His first solution called for various amounts of normal foods plus 500 gallons of vinegar. Well, imagine 2,000 of these. Well, that's a lot of vinegar. It turned out that he had forgotten a constraint, so he reformulated the problem, and his next solution called for 200 billion cubes per day. Well, that's enough to make soup for your class. Something wasn't right again. This time, he reformulated the problem with an upper limit on billion cubes, and his resulting solution this time called for 2 pounds of bran per day. That's more than a few plates of muffins. Still, there was something right about the formulation. So he imposed an upper limit on bran as well. But his next diet called for 2 pounds of blackstrap molasses. Well, imagine the size of gingerbread house. At that point, it was clear to him that it wasn't easy to generate a tasty diet with the method he developed. Your teacher is now handing out a list of all the foods that Stigler considered. If you had to restrict your diet to the set of foods, which ones would you prefer? And which ones would you try to avoid? Do you think that you could come up with a diet that will satisfy your minimum daily requirements for nutrition? I'll discuss these questions with your neighbor, and I will see you in a few minutes. Welcome back. Before moving further with solving a linear programming problem, Let's first take a step back and formulate our own diet problem. We will be cooking two Mediterranean dishes. Our first dish is called green beans. In Turkish, it's called zeytinyağlı taze fasulye. Green beans is traditionally served as cold, but it's perfect when it's warm too. One could enjoy as a summer dish when it's really hot outside. The recipe for kısır varies from region to region in Turkey. However it's made, kısır is a perfect dish to be served with an afternoon tea or as an appetizer. Well, we are done cooking, but before serving it, here comes our diet problem. Let's assume that I weigh around 120 pounds and I'm a moderately active person. So I require about 2000 calories per day. My daily requirements are 271 grams of carbohydrates, 91 grams of protein, and 65 grams of fat. This dinner will cover half of my daily requirements, so the calorie intake should be at least 1000. I should consume 135.5 grams of carbohydrates, 45.5 grams of protein, and 32.5 grams of fat from this dinner. One serving of green beans contains 12 grams of carbohydrates, 3 grams of protein, 9 grams of fat, and 171 calories, while one serving of kısır contains 33 grams of carbohydrates, 6 grams of protein, 1 gram of fat, and 150 calories. Our goal here is to have the right amounts of carbohydrates, fat, and protein from these two Mediterranean dishes while minimizing the cost. You are now given all this information summarized in a handout. Work with some other students and come up with some reasonable combinations of these two foods. Welcome back. What desirable levels of green beans and kısır did you come up with? We can easily say that we reach or even exceed our daily requirements by eating only either 16 servings of green beans or 33 servings of kısır. Let's look at these two options. First of all, what's the cost of the first option? If we were to have only 16 servings of green beans, it will cost us $32. Second, what's the nutrient and calorie intake? This option contains 192 grams of carbohydrates, 48 grams of protein, 144 grams of fat, and 2,736 calories. As seen here, even though we have the right amount of protein, we have too much of the others. The second option, to eat 33 servings of kısır, will cost us $49.5 and contains 1,089 grams of carbohydrates, 198 grams of protein, 33 grams of fat, and 4950 calories. In this case, we have the right amount of fat, but too much carbohydrates and protein. Also, who can eat 33 servings of kısır? We can't really lower it, since that will violate the daily requirement for fat. Similarly, if we were to have only green beans, we will have to eat all 16 servings. Again, that's a lot of green beans. Next, we will look at how we can model this linear programming problem mathematically. And it's a linear program because the quantity of a nutrient consumed is exactly the quantity of that nutrient that your body uses. Basically, there are no interactions between kısır and green beans, or no interactions among carbohydrates, fat, and protein. Let's continue with the mathematical formulation and denote the quantity of green beans as x1 servings and kısır as x2 servings. And let's note the cost by z. Linear programming problems can involve both equality and inequality restrictions, and the latter is the case in our diet problem. To construct the limitations or constraints, let's start with the fact that we can't really have negative amounts of food. Hence, both x1 and x2 amounts of green beans and kısır should be greater than or equal to 0. Let's look at this from a plane geometry perspective. x1 represents one dimension and x2 represents a second dimension. So we are working in a two-dimensional space. The two dimensions x1 and x2 are represented by the right angle axis. If we graph these inequalities, for x1 greater than or equal to 0, the solution space is any value of x1 that's greater than 0. Basically, any value to the right of the point 0. Similarly, for x2 greater than or equal to 0, the solution space is any value of x2 straight up from the origin, perpendicular to the x1 axis. Basically, these two constraints are used to make sure that x1 and x2 values are non-negative. Let's continue with carbohydrates. One serving of green beans contains 12 grams of carbohydrates, whereas one serving of kısır contains 33 grams of carbohydrates. We should then have the following: 12x1 plus 33x2 greater than or equal to 135.5. So we are searching for a solution space in which every point x1 and x2 yields a sum greater than or equal to 135.5. The first step is to draw the barrier line. Remember, this is a linear program, so we know that the constraints can be expressed as linear combinations of x1 and x2, and the barrier must be a straight line. In order to do this, we find 2 points, one on the x1 axis and the other on the x2 axis. If x1 is equal to 0, we must have x2 equal to 4.1. That's our first point. If x2 is equal to 0, then we have x1 as 11.3. And this is our second point. These 2 points lie on the barrier line. Since we are searching for a sum greater than or equal to 135.5, all the points in this shaded area and its boundary satisfy this inequality. Similarly, for protein, one serving of green beans contains 3 grams of protein and one serving of kısır contains 6 grams of protein. And it should be less than 45.5. Hence, the limitation on protein should be 3x1 plus 6x2 greater than or equal to 45.5. Here we mark the barrier line for this inequality too. For fat, it is 9x1 plus x2 greater than or equal to 32.5. As seen here, this inequality will eliminate even more points in our solution space. We also have a limitation on the total number of calories we intake. One serving of green beans has 171 calories, whereas one serving of kısır contains 150 calories. Since the minimum number of calories is 1000, the constraint looks like 171x1 plus 150x2 greater than or equal to 1000. Before moving further, one last but important thing I want to point out is that the constraints on protein and fat are binding, meaning that changing any one of them also changes the optimum solution. We are now finished formulating our own diet problem. Here comes the fun part. How do we solve it? In other words, how do we determine the required amounts of x1 and x2 which simultaneously satisfy these 6 inequalities? What do you think? Any ideas? Talk with your neighbors and with your teacher. See you soon. Do you have any ideas on how to solve this problem? One approach is the graphical method. The blue area here represents the combined solution space or intersection of all these inequalities. Each of the extreme points of this region corresponds to the binding of a pair of constraints. Binding here means these constraints are tied. The inequality becomes an equality. Let's further evaluate this by looking at points A, B, and C as seen here. We could have considered other points such as point D, but that's not a feasible extreme point. On the other hand, points A, B, and C are feasible. Point A corresponds to the binding of the constraints 9x1 plus x2 greater than or equal to 32.5 and x2 greater than or equal to 0. Evaluating our objective, which was z equal to 2x1 plus 1.5x2 at point A with x1 equal to 0 and x2 equal to 32.5 gives us a total cost of $48.75. Let's move to point B, which corresponds to the binding of the constraints 3x1 plus 6x2 greater than or equal to 45.5 and 9x1 plus x2 greater than or equal to 32.5. Evaluating our objective at point B with x1 equal to 2.93 and x2 equal to 6.12 results in $15.04. Our last extreme point is point C, which corresponds to the binding of the constraints 3x1 plus 6x2 greater than or equal to 45.5 and x1 greater than or equal to 0. Again, evaluating our objective at point C with x1 equal to 15 and x2 equal to 0 provides us with a total cost value of $30 that's higher than point B. Since point B results in the smallest objective value, we pick point B, which is the optimum extreme point. The optimum solution is to have 2.93 servings of green beans and 6.12 servings of kısır with a minimum cost of $15.04. Now we are done solving our diet problem. Here comes the challenge. Most linear programming problems in real life involve thousands of feasible extreme points. It would be really impractical to find all feasible extreme points and evaluate each and every one of them. That's why, as I mentioned at the beginning of the lesson, George Danzig developed this method called the simplex. It's one of the fundamental methods used to solve linear programming problems. Simplex method somehow systematically searches a small set of such extreme points and finds the optimum by always improving the value of the objective function or at least staying at its current level. You now know about linear programming and how to solve linear programming problems using the graphical method. In our lesson today, we formulated and solved the diet problem for people. Just as a note, the diet problem for chickens, cattle, and pigs has been a notable linear programming example too. In fact, it's an extension of the simple diet problem we face in our daily lives. It's used daily to purchase feed for cattle in real-time marketing cost, which is then mixed by special linear programming formulations. Here is a challenging problem for you. Why don't you formulate a nice diet problem for your cat or dog? It might be a little challenging since the simple model we just developed is one that doesn't take into account the dietary needs of a pet. Thus, it will probably require much more thought and modification to reflect the real-world situation for them. This even holds true for any person who needs to modify this simple formulation to reflect his own specific dietary needs. I hear some of you asking whether we can apply these methods to solve problems other than the diet problem in our daily lives. Yes, and of course, so many of them. There are many industries that use linear programming in their decisions they make. One example is from the entertainment industry. Theme parks such as Universal Studios use linear programming to decide on queue lines. Or most of us have probably been at one of those retail stores in a theme park. They use linear programming to determine which and how much of a product to order, which constitutes a significant portion of parks' profits. Another industry is manufacturing. For example, how do you think that a manufacturer of school bags decides how many from each style and color to make in order to maximize its profit? Most of you in the class own a school bag, right? You buy a new one because it's either old or out of style or some other reason. Based on the constraints set by the market trends, which you probably have an impact to, the manufacturer decides on how many to produce to maximize its profits. The airline industry is another one which uses linear programming to schedule their pilots, plane routes, direct and indirect flights, or to determine their ticket prices. I hope you enjoyed learning about linear programming. I also hope that you will use these methods to optimize your own daily diet. Thank you. I hope you enjoyed this lesson since it has been a joy for me to create it. Hopefully your students will enjoy it too. I have a couple things to mention regarding some of the segments. In segment 1, you might want to ask students to give other examples of programming problems they faced in their daily lives and what their approaches were to solve them. In segment 2, students need to have some prior knowledge of permutations. If your curriculum doesn't cover it, one way might be to assign some homework problems before the lessons. Or you could work through some examples in the classroom the day before this lesson. There is actually an excellent source as lecture notes on the fine art of counting. It's available online on MIT's OpenCourseWare website. You could also further explain the term linear with some additional examples, since most students in your classroom might have never seen it. A potential source might be Hillier and Lieberman's book called The Introduction to Operations Research. In segment 3, a great idea to enhance students' knowledge on the history of linear programming could be handing out the articles by Stigler, Danzig, and Strauss for further reading following this lesson. For these articles, please refer to the additional online resources section. Regarding the material in segment 4, some of your students might actually enjoy doing additional reading on nutrition facts and dietary guidelines. This information could be found on the websites of the U.S. Department of Agriculture, the U.S. Department of Health and Human Services, and also Food and Drug Administration. Segments 6 and 7 explain solving our diet problem using the graphical method, thus involve a lot of geometry. To make sure that your students feel comfortable with graphing equations, you could assign homework problems before this lesson. Also, students probably need graphing paper while working in groups in the classroom. In segment 8, there is some terminology being used which your students might have never seen before. So to better prepare them, you might want to explain the terms such as extreme point and feasible in further detail. John Chignek's notes on linear programming explain some of this terminology through the prototype example of the Acme Bicycle Company. If you also want to further explore linear programming in the classroom, you could work on other prototype examples such as product mix, resource allocation, workforce scheduling, blending or mixing problems, and aggregate planning. In the additional online resources section, we provided some useful links to those prototype problems. You could also go into greater depth on the solution methods for linear programming. We have included in the supplementary material how to solve our diet problem using the simplex method. You could either spend another class period on the simplex method or provide this supplementary material as a handout for students to read after the lesson. For other methods such as the revised simplex method or the transportation problem algorithm, John Chignek's notes on linear programming in practice might be a good source. Further information is again provided in the additional online resources section. Before we end our lesson today, I would like to thank Professor Saul Gass for all that he has done in teaching linear programming and also for letting us use his ideas from his book, An Illustrated Guide to Linear Programming in this video. Thank you for your interest in this lesson. I hope it helps making the topic of linear programming exciting to your students. I wish you the best of luck.